तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we were considering permutations and combinations. What is a permutation and what is a combination? The combination of R objects out of n objects, which is selecting R objects out of n objects, is denoted by C n R, and the formula for that is n factorial by n minus r factorial into r factorial. This we have seen in the last lecture. And what is a permutation or arrangement of R objects out of n objects? It is denoted as PNR, the permutation of R objects out of n objects, and the formula for that is n factorial by n minus r factorial. This also we have seen in the last lecture. We have also seen some other formulae. For example, if you have n objects, out of which q1 of them are of the first kind, q2 of them are of the second kind, and so on, and qt of them are of the tth kind, then the number of permutations you are q1 of them are identical, q2 of them are identical, qt of them are identical, and out of these n objects, then the number of permutations we can have is denoted by n factorial by q1 factorial, q2 factorial, qt factorial. This also we have seen, some other formula also we have seen. So, the same sort of idea we are going to consider today in a different manner. We are going to consider the distribution of non-distinct objects into distinct cells, and we are also going to consider the distribution of distinct objects into distinct cells. So, there are two things we are going to consider today: the distribution of distinct objects into distinct cells and the distribution of non-distinct objects into distinct cells. Let us first consider the distribution of distinct objects. We can see that there will be close correspondence between this and permutations and combinations. So, first considering the distribution of distinct objects, you are having R distinct objects and n distinct cells. Now, n may be greater than or equal to R, or n may be less than R. So, depending on the two cases, you have different formula. The result is like this. Let us see how we get this in a moment. There are PNR or PRN ways to place R distinct objects into n distinct cells, where each cell can hold only one object, depending on whether n is greater or less than R. So, you are having R objects, they are all distinct, say A1, A2, AR, and you are having n cells, they are also distinct. These are objects are all distinct, cells are also distinct. Say so, in how many ways can you distribute them into these cells so that one cell can hold only one object. Now, there are two possibilities. N may be greater than R equal to R, or N may be less than or equal to R. So, in these two cases, what are the results? Now, when N is greater than or equal to R, you choose, take the first object, you choose one cell and put it in that. That can be done in n ways. After one cell can contain only one object. So, after selecting one cell, you should not consider that cell again. So, after that take the second object, there are n minus 1 cells remaining. So, the second one you can put in any one of the n minus 1 cells. So, that is n minus 1. Then take the third object, that can be put in any one of the remaining n minus 2 cells. We are considering the case when n is greater than or equal to R. So, that will be n minus 2 and so on until the rth object, when you take it, there will be n minus R plus 1 cell remaining. You can put it in any one of them. We are considering a case when n is greater than or equal to R. So, the last object you can put in any one of the n minus R plus 1 cells. So, this is the product you obtain, and we know that this is nothing but n factorial by n minus R factorial, and that is just P n R. Now, consider the case when R is greater than or equal to n. In this case, we get the result as PRN. Let us see how we get this. There are R objects now and n distinct cells. Objects are distinct, cells are also distinct. And how do you fill them? One cell can contain only one object. So, take the first cell. You can put one of the R objects into this. Select one of them and put it in the first cell. That can be done in R different ways. After doing that, you are left with R minus 1 objects. Pick one of them and put it in the second cell, and that can be done in R minus 1 ways. And after doing that, you are left with R minus 2 objects. Take the third cell and pick one of them and put it in the third cell. That will be R minus 2. And the last object or the nth cell can be filled in R minus n plus 1 ways by selecting one of the R minus n plus 1 objects. And this reduces to R factorial by R minus n factorial, which is nothing but P R n. So, you see the connection between the permutation of R objects out of n objects, or in the other case n objects out of R objects, and see how this is related to the way of filling n distinct cells with R distinct objects. And we have considered the two cases where n may be greater than or equal to R or less than or equal to R. So, this is one result. We are not allowing any repetition, that is, one cell can contain only one object. When one cell is allowed to have more than one object, what happens? The distribution of R distinct objects in n distinct cell, where each cell can hold any number of objects, is equivalent to the arrangement of R of the n cells when repetitions are allowed. How do you get this? You are having R distinct object, n distinct objects. Now, each cell can contain any number of objects, you are not putting any restriction on that. In that case, what happens? Take the first object, you can select any one of the n cells and put it there. Take the second object, you can select any one of the n cells, put it there. Take the third object, you can select any one of them and put it there. Because repetitions are one cell can contain more than one object. Like that, the rth object also you can select any one of the n cells and put it. So, this becomes equal to n power r. We are not saying anything about n greater than or equal to r or less than or equal to r. In both cases, the result is the same. It is equal to n power r. When the order of the objects in a cell is also considered, what is the number of ways of distribution? For example, again in this case we are having r distinct objects and n distinct cells, but now each cell can contain more than one object, and the order in which you are putting the objects in a cell is important. For example, suppose I select A1 and put it here. Then I select A2 and put it here. Then I come to A3, I want to put it in this cell, but I can put it like this or I can put it like this. So, the order becomes important. In that way, what is the answer? You see, this is the number of ways of selecting r objects out of n objects where repetitions are allowed. So, the answer will be like this. It will be n plus r minus 1 factorial by n minus 1 factorial and given by this. How do you get this? It is like this. Take the first object, you can put it in any one of the n cells in n different ways. Suppose I put it in this. Take the second object, I can put it in any one of the remaining n minus cells, or if I want to put it in this cell, it can be prior to this or after this. So, actually there are n plus 1 ways of putting the second object in the n cells. Having done that, take the third object, suppose I put it here, then there are n minus 2 ways of putting in the vacant cells, and here there are 2 ways, here there are 2 ways. If I want to put it here, I can put it here or here I can put it here or here. So, that will amount to n minus 2 plus 2 plus 2, that is n plus 2 ways of filling it. Supposing A1 and A2 have been put in the same cell, say A1, A2, then the third object when I take, I can put it in any one of the n minus 1 cells, or if you want to put it in this cell, I can put it here, I can put it here, I can put it here. There are 3 ways of putting it in the same cell, that will be n minus 1 plus 3, which is n plus 2 again. So, when I take the third object, I can fill it in, I can put it in n plus 2 ways in any one of the n cells, where each cell can contain more than one object, and also the order of the objects in the cell is taken into consideration. Like that proceeding, the rth object can be put in n minus r plus n plus r minus 1. The rth object can be put in n plus r minus 1 ways. So, that will become equal to n plus r minus 1 factorial by n minus 1 factorial. So, this is how we get this result. Immediately you consider a problem. What is this? What is the number of ways of arranging 7 flags on 5 masks when all the flags must be displayed, but not all the masks have to be used? You are having 5 masks and you are having 7 flags. In how many ways can you display them, where you need not have to use all the 5 masks, but all the 7 flags you have to display. Take the first one, I will call them as F1, F2, F7. Take the first flag, I can put it in any one of the 5 masks in 5 different ways. Having done that, take the second flag. Suppose I have put the first flag here. Take the second one, I can put it in 1, 2, 3, 4, any one of the 4 masks, or if I want to put it here, I should put it before this or after this. There are 2 possibilities. So that can be done in 6 ways. And the third flag I can put in 7 ways. Then the fourth one I can put in 8 ways. The fifth one in 9 ways. The sixth one in 10 ways. The seventh one in 7 ways. So these 7 flags can be put in the 5 flags in 5 into 6 into 7 into etc. up to 11. That is equal to 11 factorial by 4 factorial. Or here what is n? Here in this case n is 5, r is 7. So what is the formula? The formula is n plus r minus 1 factorial by n minus 1 factorial. So the formula is n plus r minus 1 factorial by n minus 1 factorial, that is 5 plus 7 minus 1 factorial by 5 minus 1 factorial, which is the same as 11 factorial by 4 factorial, and we have got the result like this. So this example exactly illustrates what we considered earlier. Now the distribution of n objects, q1 of them are of one kind, q2 of them are of one kind, and so on. What is the formula for this? You want to distribute n objects into n cells, where q1 of them are of one kind, q2 of them are of one kind, and qt of them are of kind, into n distinct cells. Here please note that the number of objects and the number of cells are the same. So you are having n objects and n cells. Cells are distinct, they are distinct, but objects q1 are of them of the first kind, q2 of them are of the second kind, and so on, qt of them are of the tth kind. That is, in essence, what you are considering is you are permuting n objects, out of which q1 of them are identical, q2 of them are identical, and q3 of them are identical, and so on. This distribution in essence means that you are permuting n objects, you are arranging n objects where q1 of them are identical, q2 of them are identical, and qt of them are identical. The formula for that is, you know, is n factorial by q1 factorial, q2 factorial, qt factorial. This is the formula for that, which we have seen in the last lecture. Thus, the number of ways of distribution is n factorial by q1 factorial, q2 factorial, qt factorial. The same formula you can also derive in a slightly different way. How do you do that? Among the n distinct cells, you have to select q1 of them. We have c n q1 ways to pick q1 cells for the objects of the first kind. After having done that, you are remaining with n minus q1 cells, out of which you have to pick q2 cells, and that can be done in c n minus q1 comma q2 ways to pick q2 cells for the objects of the second kind, and so on. In that case, what happens? Let us see what happens. So, you are having n objects and n cells. So, we want to select q1 cells out of these n cells and put the objects of the first kind, and that can be done in C n comma q1 ways. After having selected q1 cells, we are left with n minus q1 cells, out of which we select q2 of them to put the second type of objects. After having done that, we are left with n minus q1 minus q2 cells, out of which we select q3 of them to put objects of the third kind, and so on. And finally, you are left with n minus q1 minus qt minus 1 cells, in which you put the objects of the tth kind, qt. But this is nothing but qt, that you must remember. So, having done that, let us expand and see. This will come to n factorial by n minus q1 factorial into q2 factorial. This will be n minus q1 factorial by n minus q1 minus q2 factorial into q2 factorial, and so on. And the last one will be n minus q1 minus q2 minus qt minus 1 factorial by n minus q1 minus q1 up to qt factorial into qt factorial. This will be the formula. Now, you can see that this will cancel out with this one, this will cancel out with this one, and so on, and this will cancel out with the previous term, and this is nothing but 0 factorial, which is taken as 1. So, the answer you get is n factorial by q1 I am sorry, this is q1 factorial, q1 factorial, q2 factorial, and so on up to qt factorial. Now, in this case we have taken n objects and n cells. The n cells are distinct, but the objects are of this type. Now, instead of taking n objects, if you have taken r objects, what will be the formula? And that is given by this. So, the number of ways of distributing r objects where n is greater than or equal to r, with q1 of them of one kind, q2 of them of another kind, etc. into n distinct cells is Cn q1, Cn q1 q2. The same argument holds here also. But in the last case, the same way you have to argue out. In the last case, we have taken this as 0 factorial, but that will not be 0 factorial. Q1 plus Q2 plus Q3 up to Qt is equal to R. There are totally R objects, and Q1 of them are of one kind, Q2 of them are of one kind, and so on. So, Q1 plus Q2 plus Q3 up to Qt is equal to R. So, instead of this, you will get n minus R. So, the answer in this case will be n factorial divided by Q1 factorial, Q2 factorial, Qt factorial into 1 by n minus R factor. So far, we consider distribution of distinct objects into distinct cells. We consider R distinct objects and n distinct cells, and we considered the case where each cell can contain only one object, and we also considered the case where each cell can contain more than one object, and so on. And we also considered the case where all the R objects are not different, but Q1 of them are one kind, Q2 of them are another kind, and so on. Next, let us consider non-distinct objects and distinct cells. Let us see what is the result. So, we want to distribute non-distinct objects into distinct cells. So, what you are having is, you are having n distinct cells or non-distinct objects. You are having n cells, distinct cells, and you are having identically R object, and we take n to be greater than or equal to R. N is greater than or equal to R. Then there are CNR ways of placing R non-distinct objects into n distinct cells with at most one object in each cell. So, you can put only one object in each cell. So, with that restriction, if you see, you will realize that out of the n cells, you have to select R of them and put the objects in those cells. So, you are selecting from the n cells R cells. So, that is equivalent to saying CNR, number of ways of selecting R objects out of n objects. So, here you are selecting R cells out of n cells, and that is can be done in CNR ways. So, there are CNR ways of placing R non-distinct objects into n distinct cells with at most one object in each cell. Now, if a cell can contain more than one object, what is the formula? The number of ways to place R non-distinct objects into n distinct cells where a cell can hold more than one object is given by this. How do you get this? See, when two or more objects are put in one cell, the order does not matter here, because what happens? All the objects are identical, so the order in which you put them in one cell does not matter. So, you have to really select R cells out of the n cells, but here repetitions are allowed. So, this is equivalent to saying the number of ways to place R non-distinct object into n distinct cells. This is equivalent to saying, or this is equivalent to the number of ways of selecting R cells out of the n cells where you allow for repetition. And from the earlier lecture, we know that the number of ways to select R objects out of n objects where you allow for repetition is given by this formula, C n plus R minus 1 comma R. So, because of this formula, you get that the number of ways to place R non-distinct objects into n distinct cells is given by this. Now, here you are also allowing the case when a cell can be empty, or you are not selecting a cell or putting an object. But if you do not allow that, you allow that each cell should contain at least one object. So, you put the restriction that none of the cells can be empty. So, if you put this condition, if none of the n cells can be left empty, then what is the number of ways of distributing R objects into n distinct cells where the objects are all identical? Here, if you do not want any one of the n cells to be empty, that means R must be larger than or equal to n. Okay. So, in this case R is greater than or equal to n. Here the number of ways of distribution is given by this formula CR minus 1 n minus 1. How do you get this? Now, you are having R objects and n cells. First you select n of them, they are all identical. So, you just pick n of them and put one each. Then you will be left with R minus n objects. First you are selecting n objects and then putting one in each one of the cells. Then you are left with R minus n objects. The objects are identical. Now, you want to put them in the n distinct cells, and by the formula this will be equal to C R minus n plus n minus 1 comma R minus, because the formula is, you know, that C R minus R plus n minus 1 comma R. This is the formula. Now, instead of R you are having R minus n. So, in this place you are having R minus n, and in this place also instead of R, this is the original formula, and because you have taken out n objects and put in each one of the cells, you are left with R minus n objects. So, in this formula you have to replace R by R minus n and R minus n here also. So, this will reduce to C R minus 1 comma R minus n, this is equal to this, and C, you know this formula, C n R is equal to C n n minus R. Why? The number of ways of selecting R objects out of n objects is equivalent to the number of ways of rejecting n minus R objects out of n objects. So, this is equal to C R minus 1 comma R minus 1 minus this will be n minus 1. So, you get this formula. So, that is what this portion says. We can first distribute one object in each one of the n cells and then distribute the remaining R minus n objects arbitrarily. The number of ways of distribution is given by this, which is equal to C R minus 1 R minus 1, which is also equal to C R minus 1 n minus 1. Now, a direct extension of this result is, instead of putting the restriction that each cell should contain one object, suppose I put the restriction that each cell should contain q objects, then what happens? So, we want to put the restriction that each cell should contain q objects. So, first you pick out q objects, they are all identical. So, put q of them here, q of them here, q of them here. So, you have taken out R minus nq objects and put them in q in each one of the cells. So, you are left with R minus nq objects. You have taken out n into q objects from this and put q in this and so on. So, you are left with R minus nq objects. These R minus nq objects you can distribute among the n cells in an arbitrary manner. So, in the formula C R plus n minus 1 R, instead of R Now you have to put R minus NQ. So the formula will be C R minus NQ plus N minus 1 comma R minus NQ, and that will be equal to C R minus NQ plus N minus 1 comma N minus 1 because of this result. C n R is equal to C n N minus R. So you get this result. This is a number of ways of doing that will be C R minus NQ plus N minus 1 comma R minus NQ, and instead of this you can write N minus 1 if you want. So we have considered distribution of R non-distinct objects into N distinct cells. Now let us consider a problem immediately after this. In how many ways can 2n plus 1 seats in a congress be divided among 3 parties so that the coalition of any 2 parties will ensure them a majority? So you are having, say, in assembly seats or parliament, something like that, you are having 2n plus 1 seats and 3 parties are contesting for them. Each party may win some seats, and for formation of the government the number of seats should be such that it should be possible for any 2 parties coming together and form a government. So suppose the 3 parties are P1, P2, P3. It is like you are having 3 cells, 3 distinct cells, 3 distinct parties are there. The seats there is no distinction, so it is identical objects. You are having 2n plus 1 identical objects and you want to distribute them among these. So in how many ways can you distribute these 2n plus 1 seats between 3 parties? Here R is equal to 2n plus 1, n is equal to 3. So the formula is C R plus n minus 1, that is 2n plus 1 plus 3 minus 1 comma R, that is 2n plus 1, that is equal to C 2n plus 3 comma 2n plus 1, this is also equivalent to C 2n plus 3 comma 2. This is the number of ways in which the 2n plus 1 seats can be distributed between the 3 parties. But there is one more condition here, that is any 2 parties combining together should be able to get a majority. Majority will be n plus 1 or more. Now suppose this gets more than n plus 1 seats. In that case, these 2 together will get less than n seats, and in that case these 2 together will not be able to form a government. The condition is the distribution of the seats between the 3 parties should be in such a way that any 2 parties combining together should be able to form a government. So out of the general number of distributions which is given by this, you have to subtract those distributions where one party gets more than or equal to n plus 1 seats. So what is that? Suppose I have P1, P2, P3 like this. N plus 1 seats are already given to P1. The remaining n seats are distributed between P1, P2, P3. In how many ways can you do it? You can do it in C into the number of seats is now R. So, R is equal to n now, n is equal to 3. So, what is the formula? The formula is C n plus 3 minus 1 comma n, and that is 3 C n plus 2 comma n, which is equal to C n plus 2 comma 2. So, the number of ways in which P1 gets n plus 1 seats or more is given by this formula. This should be subtracted from the total number of distributions available, and similarly P2 can get n plus 1 or more seats. That should also be avoided. So, that is again the number of ways in which P2 gets n plus 1 or more seats and the remaining seats are distributed between P and P3 is again the same number, and a similar case holds for P3 also. So, the total number of ways in which the seats can be distributed among parties such that any two of them will be able to combine and form a government is given by C 2n plus 3 comma 2 minus 3 times C n plus 2 comma 2. And what is this? This is 2n plus 3 into 2n plus 2 by 2, and this is n plus 2 into n plus 1 by 2. If you simplify, this will be half into n plus 1 into 2 into 2n plus 3 minus 3n plus 2, and that will be half into n plus 1. This is 4n plus 6, this is minus 3n plus 6 will be just n. So, the answer is half of n into n plus 1 or n into n plus 1 by 2. This is the number of ways in which you can distribute the seats, or the parties can be given the seats such that it is possible for any two of them joining together and form a government getting a majority of n plus 1 or more. Now, what will happen if the same argument is given, but instead of 2n plus 1 seats, see in 2n when you have an odd number of seats, it is very easy. You have a majority of n plus 1 or more is majority. Now, the same if you have an even number of seats, say 2n seats you are having, majority will be n or n plus 1 or more you must get. So, what will happen if you, so you have to use the same formula. If you have 2n seats, the number of ways of distributing the 2n seats among the three parties, you have 2n seats, you have to distribute them among the three parties. In this case, this formula if you apply, it is R will be 2n, n will be 3. So, you will get 2n plus 3 minus 1 comma 2n, and that will be 2n plus 2 comma 2n, or that will be C 2n plus 2 comma 2. Now, you have to avoid cases where P1 gets n, if the remaining gets n, then also they cannot combine and form a government. So, when P1 gets n and the remaining n are distributed among the 3, such a distribution will not help to form a government by P2 and P3. So, using the same formula, supposing P1 gets more than or equal to n seats, what is the number of ways of distribution? That is, in this case, the remaining n can be distributed among the 3. So, what is n? N is 3. What is r? R is n. So, the formula is C n plus 3 minus 1 comma n, which is C n plus 2 comma n or C n plus 2 comma 2. So, the formula in this case, again the same thing you have to consider for P2, you have to consider for P3. So, the formula here is the total number of ways is total number of ways of distribution this is given by C 2n plus 2 comma 2 minus 3 times. This is the formula where P1 gets n or more seats. Similarly, for P2 and P3. So, you get 3 times C n plus 2 minus 2 plus 3. Why do I get plus 3 in this case? So, in the last example when I considered, we did not consider this plus 3, but here we have to consider plus 3. The reason is I am considering this formula. See, this is when P1 gets n or more objects. When P1 gets n objects and P2 gets n objects and P3 gets 0 objects, this will be accounted for once in this formula. It will also be accounted for when you consider the formula for P2 getting n or more objects. So, this one will be accounted for more than once, it will be accounted for twice. Similarly, the distribution for P1, P2, P3, this distribution and this distribution and this distribution, each one of them will be accounted for 2 times in this. You should not subtract twice that. So, that is why we are adding 3 and this will give you the answer. This will be 2n plus 2 into 2n plus 1 by 2 minus 3 into n plus 2 into n plus 1 by 2 plus 3, and if you simplify this will be half into n plus 1. If you take out, this will be 4n plus 2 minus 4n plus 2 minus 3n minus 6 plus 3. If you simplify, this will be equal to half into n minus 1 into. So, we have seen that what is the number of ways of distributing R distinct object into n distinct cells and also R non-distinct object into n distinct cells, and how this concept can be used to solve some problems. Let us consider 1 or 2 more problems in permutations and combinations. Let us consider this problem. Prove the identity 1 into 1 factorial plus 2 into 2 factorial plus n into n factorial is equal to n plus 1 factorial minus 1. Discuss the combinatorial significance. Now, you know that 1 into 1 factorial is equal to 1 plus 1 into 1 factorial minus 1 factorial. 2 into 1 factorial minus 1 factorial, that is 2 factorial minus 1 factorial, 1 into 1 factorial. 2 into 2 factorial is like that, you can say it will be 2 plus 1 into 2 factorial. Instead of 2, I am writing it as 3 minus 1. So, this is 3 plus 1, 2 plus 1, 2 factorial minus 2 factorial. That is equal to saying 3 factorial minus 2 factorial. Proceeding like this, n into n factorial will be n plus 1 factorial minus n factorial. So, add all these things, you will get the left hand side. So, if you add all, you get the left hand side of this, left hand side 1 into 1 factorial plus 2 into 2 factorial etc. up to n into n factorial. But you see that this minus 2 factorial will cancel with this. The next term will be 4 factorial minus 3 factorial. So, this will cancel with this and so on, and this n factorial will cancel with previous term. So, this will reduce to n plus 1 factorial minus 1 factorial, that is equal to n plus 1 factorial minus 1, which is the right hand side. So, you have proved the inequality. Here we have not used any combinatorial argument. We have just used the formula and shown this. Now, what is the combinatorial significance of this? Consider n plus 1 objects A1, A2, A n plus 1. You are having n plus 1 objects and you are permuting, you are arranging them in non-possible ways. What is the number of ways of arranging? That will be n plus 1 factorial. Out of which you remove the permutation where A1 occurs in the first place, A2 occurs in the second place, A3 occurs in the third place, and An plus 1 occurs in the n plus 1th place. You remove this permutation, that will be n plus 1 factorial minus 1, that is the right hand side. How do we get it? In a different way. Among the set of permutations, you consider the permutations where A1 occurs in the first place, and A1 does not occur in the first place. The set of permutations, the total number of set of permutations, you can divide into two parts like this. A1, I will say total. A1 occurs in the first place and A1 does not occur in the first place. If A1 does not occur in the first place can be filled in n ways. After filling the first place with other things than A1, you will be left with n objects, and the rest of the n places you can fill them in n factorial ways. So, that is equal into n factorial. Now, consider the case where A1 occurs in the first place. In this, you can split into two ways. A2 occurs in the second place, A2 does not occur in the second place. You have filled the first place. So, if I consider the n plus 1 places like this, first one now you have filled with A1. So, second one you should not have A2. After leaving out A2, you are having n minus 1 objects, and you can fill with any one of them this place. That can be done in n minus 1 ways. After doing that, you have filled these two places with two objects. So, you are left with n minus 1 objects. The remaining n minus 1 places can be filled in n minus 1 factorial ways. So, the number of ways in which A1 occurs in the first place and A2 does not occur in the first place is given by this. Now, you have the combination, or you have the permutations where A1 occurs in the first place and A2 occurs in the second place. This again, after putting A1 here and A2 here, the remaining n minus 1 places can be filled in different ways, that you can split like this. A3 occurs in third place, A3 does not occur in third place. And if A3 does not occur in the third place, this can be filled in n minus 2 ways, remaining n minus 2 factorial, n minus 2 into n minus 2 factorial. So, you see that proceeding like this, you get the left hand side, n into n factorial plus n minus 1 into n minus 1 factorial plus n minus 2 into n minus 2 factorial, and so on. So, the total number is equivalent to the number of ways in which you can arrange all the objects, but in which you are removing from that the permutation where A1 occurs in the first place, A2 occurs in the second place, A3 occurs in the third place, and An plus 1 occurs in the nth place. And in a similar manner, you can give a very simple explanation for this problem also. Look at this. This can be also proven in a very simple manner. For all these calculations, when you use the computer, you have to use or you have to calculate n factorial. It is very difficult and time consuming, or I would not say difficult, it is time consuming to calculate n factorial in a manner 1 into 2 into 3 and so on, rather than you use an approximation which is called Stirling's formula, and it is given by this. N factorial is given by square root of 2 pi n into n by e to the power of n. You use this formula for calculating n factorial when you want to use the computer. So, in this lecture we have seen distribution of R objects into n cells. Cells are distinct, but the objects could be distinct or non-distinct. We have considered the formulae for them. We have also seen the correspondence between them and permutations and combinations. In the next lecture, we shall see about generating functions, a concept which comes very handy in finding out the number of combinations, number of permutations, etc.